Hello everyone. So let's start today. So can you see my screen?
Yeah.
Okay, great. So yeah, we will finish today the second part of edge detection today. And so before we begin, do we have any questions like the lectures we have covered so far or from the homework assignment one? All right, so no questions. That's good. So let's do a quick recap because I think it's have been like more than 5 days. So last lecture we discussed if we have a signal F and there is some noise present in that signal, then if you want to detect edges in such a signal, what we do is first we use like a filter. For example, in this case, we have a Gaussian filter, and then we can convolve these two. This will smooth out like all the noise present in the signal. And then if we compute first order derivative of that filtered signal, we can get the edges, and edges can be extracted by extracting the peak in the signal. So these peaks could be like positive as well as negative. And we also discussed that we can perform all these operations like in fewer steps. There is optimization. So given a signal, what we do is instead of using the filter directly on the signal, we compute the derivative of the filter, Gaussian in this case. So this is like Gaussian derivative of the Gaussian. And then we convolve this computed derivative with the original signal, we will get the same result. So today we are going to discuss two basic edge detectors. These are called Prewitt and Sobel edge detector. And both of these detectors have like the same steps which we will follow. So first we'll have to smooth the signal. We can choose like any filter we want. Then we will compute derivatives. So for images, we'll have to compute derivative first in the x direction, then in the y direction. And then based on like these derivatives in these two directions, we'll have to compute the magnitude of the gradients. And then we'll use a threshold value on that gradient, which will give us like the resultant edges. So let's quickly recap like how we compute derivatives for images. So for discrete 1D signal, this is like the backward difference. We can compute the forward difference, and this is like the central difference. And these three operations can also be represented using three different masks. So we have -1 and 1, 1 and -1, and -1, 0 and 1. So what we can do is we can directly apply these masks on signals to get the derivatives. Now, if we look into images, so let's say we have an image f, which is a function of x and y, that's in 2 dimensions. So we'll have to compute the gradient vector. First, we'll have to compute the gradient, the partial derivative in x direction, and then the partial derivative in the x direction, in the y direction. That will give us like two vectors here. These vectors are like for the gradients which we have computed in x and y directions. And using these two gradient vectors, we can compute the magnitude of the gradient. So this will just be square root of fx square plus fy square. And we can also compute the gradient direction. This is a tan inverse fx over fy. Now, in the first, these two edge detectors, which we are going to discuss, we will only use the gradient magnitude. We are not going to use the direction. But at a later stage, when we will discuss like another edge detector, which is like more advanced, we will see how we can also make use of this gradient direction. So let's have a look at this Prewitt edge detector. So given an image, the first step is to perform smoothing, which will give us the blurred image. Then we will find the derivative in the x direction. This will give us edges in the x direction. Similarly, we will perform the smoothing in y direction to get the blurred image. Then we will find derivatives in the y direction. That will give us like edges in y direction. Now for smoothing, this can be like our smoothing filter. And this is the mask which we use for gradients in x direction. Now what we can do is, instead of performing these two steps separately, we can combine these two. So we can use this filter if you multiply these two. Similarly, in y direction, that's the smoothing filter. That's the filter for derivative. If you combine these two, we get this filter, which can directly use to derive the edges. Now that was a Prewitt edge detector. If you look at Sobel, it's almost identical, and some of you might like not see any difference. So you'll have to smooth, you get blurred, you compute the derivative in x direction, get the edges. Same with the y direction, and these are your filters. The only difference is when you are performing smoothing, you give like a higher weightage to the center pixel. So earlier in the Prewitt edge detector, you had like 1 at these locations, and same with the filter for the y direction. That is the only difference, and which causes like which gives you a different filter, 2 and -2 here, and in the y direction you have 2 and -2. Apart from these two, like there is no difference between the Prewitt edge detector and Sobel edge detector. Both are identical. Okay, so let's have a look. So this is a simple example. You have an image. This will give you the derivative in x direction, derivative in y direction. Then you can compute the gradient magnitude using this formula. And based on some threshold, you can get the edges. Okay, so this is a sample image. So these are like, this plot is showing the actual gradients computed on this image in the x direction. And these are the gradients in the y direction. Now, next step is to like compute the magnitude. So wherever you're seeing like these higher values, higher pixel values, those are the edges. The black areas are like non-edges. And then let's say you use a threshold of 100, then you make like everything below 100 0. That will give you these kind of edges. Okay. Now we also discussed this precision recall curve in the last lecture. So if you look at Prewitt and Sobel, the performance of both the filters is almost identical, 0.48. I mean, there are some differences like in the recall values at different thresholds, but more or less they are almost identical. And you saw that they should be, because the only minor difference is the smoothing filter you are using. So that was like the basic Sobel and Prewitt edge detectors. Now let's move on to some more advanced edge detectors. So before doing that, let's try to see how we can use second derivative for edge detection. So far we have just used first derivative. So in first derivative, as you all know, that we just have to look into maxima or minima, and those maxima minima are like your edges. So for example, if these two signals are your edges, so one edge over here, one edge over here, then you can represent this image using this signal, something like this. All right. Then if you compute derivative of this signal, you will get something like this. So you have an edge over here, you get a maxima. Then you have a edge where you're going like from higher value to lower value, so you get a minima. Similarly, you have like just the opposite of this. So now based on this maxima and minima, you can extract these edges. You'll have to put some threshold. Now let's like find the second order derivative of this signal. So this is showing the second order derivative of this signal. Here you can see that you get a maxima, then suddenly a minima. So for each maxima, you will get a maxima and minima in your second order derivative. And that's happening because for this particular maxima, your slope is increasing, and your second order derivative gives you like rate of change of your slope in the signal. So that's why it's increasing. And suddenly the slope is going down which is like giving you this minima. Now, if you observe carefully like the second order derivative, then you can also use the second order derivative to detect your edges. So for that, what you will have to do is whenever your second order derivative is crossing like from positive to negative, so in this case, at this location, and in this case, it's like going from negative to positive, so you will have an edge. And that's how you will use a second order derivative for edge detection. So these crossings are called zero crossings. And so one edge detector which uses second order derivative is Marr Hildreth edge detector. And so the steps we follow in this edge detector are, first we have to smooth the image. So in this case, instead of using a smoothing filter or the average filter, we'll make use of Gaussian filter. So that's one difference. Then we'll have to apply Laplacian, and this is like a second order derivative. So this is a widely used operator, and I think you all must already know what Laplacian is. And then we'll have to find zero crossings. So for zero crossings, first we'll have to like scan across along the x-axis, and then we'll have to repeat that along the second axis. All right, so one big difference was instead of average smoothing, we are doing Gaussian smoothing. So given an image, you take a Gaussian filter that image, you will get like the blurred or the smooth image. And this is your Gaussian filter in two-dimensional. So that's like the continuous filter. This is like the discrete filter, which you will actually use. That's just like the Gaussian equation, which was used to find these values here. Now, the second step is to find the Laplacian, and Laplacian is nothing but you have to compute second order derivative, partial derivative with respect to x, and then you have to compute second order partial derivative with respect to y. You just add up these values, that will give you the Laplacian. Okay. Now, so one important point here is like not an important point, just a minor notation. So this we earlier used for gradient when you compute the derivative. And this is like the inverted triangle, which is used for this Laplacian. So don't confuse between these two. Both are different things. Now to find the zero crossings, let's see like what are the different cases. So the first case could be, we might be moving from a positive value to a negative value, then we will cross a zero. The other could be, we are again moving from positive to negative, then we might also be getting a value of zero. So this is like an easier case. Same like case for the, just if you reflect these two, will move from negative to positive via zero. So these are the four cases when we will observe zero crossing in our signal. And what we have to do is, we'll have to compute the slope at these zero crossings. So for a and negative b, you can just add these values. That will give you the slope. And again, what you do is you will compute the slope and use some threshold on that slope. So if the slope is like very high, you will consider that as a zero crossing. If it's not that high, it will not be a zero crossing. So earlier when this filter was proposed, it was a big deal that they were saying they don't need any thresholds, which was actually required for first order derivative when you have to use the threshold to figure out whether this is a maxima or minima. But eventually they were also using this threshold to find the slope. And it's just that it's less sensitive to noise, so it was performing better. Okay, so let's look at like how you can compute this second order derivative. So this is your image, this is your Gaussian filter. So you compute the Laplacian of this Gaussian, then convolve with image. Now, this is a normal Gaussian equation. So if you find the partial order derivative of this Gaussian in both x and y direction, and when you will add those, you will get this equation. So we are not going to prove this in the class. And if you're interested, what you can do is we have like referenced 2 books for this classical computer vision. So I think in the first one, in chapter 3, you will have this proof. And in the second book, I think it's in chapter 2. So if you're interested, you can go ahead and work through this proof. It's not very difficult. Now, if you compute the Laplacian of Gaussian, this is something which you will get. And this is called like inverted Mexican hat. So if you flip this like upwards, it will exactly look like a Mexican hat. All right, so this is your Laplacian of Gaussian filter. So if you compute the discrete values by feeding in like values of x and 0, these are the values which you will get. So you can see that first your values are increasing, then becoming negative, and so here they will close to 0, then they are increasing, and they are going to like local minima here. So at the center you have this negative edge. So this is exactly like this kernel. First it's 0, going positive, then dropping a lot. Okay, so these are like the discrete values. So this will be the filter which are going to use for filtering. Now, earlier we discussed that we can separate like your Gaussian or any other filter in two 1D filters. So if you have a image and you are going to convert with a Gaussian, a 2D Gaussian, in this case, what will happen is, since your filter is like it's a 2-dimensional filter, right? So at each location, if you are going to filter a pixel value, we'll have to perform n square multiplications, and n is like the size of the filter because you'll have n square values in this filter. So what you can do is you can optimize this operation, and an easy way to understand that is, so this is your Gaussian equation. So it is like exponential of this term, and this term includes like summation of these two values. So I mean, you can easily break this down into 2 exponentials, because you know that exponential of sum of 2 values, you can represent them as multiplication of 2 numbers. So this is like the first part coming from here. This is the second part. And then what you can do is you can first apply filtering using the first component to the image. So this is like the x component. And then you can apply the second component, which is the y component. And so in this way, what will happen is this is 1-dimensional filter, and this is also 1-dimensional filter. And again, the size will be n. So this operation will have n multiplications. Again, this operation will have n multiplications. So in total, you will have just 2n multiplications. And these will be like your filters in x and y direction. Similarly, you can optimize like your Laplacian of Gaussian operator. But one big difference is you cannot break it down into like 2 1D convolutions. You'll have to break it into like 4 1D convolutions. So for example, this is the operation, right? So this is your Laplacian of Gaussian. It will require n square multiplications, again, because the size of this filter is n by n. Now, what you can do is you can break this down into these 4 operations. And again, we are not going to prove this in the class. The proof is in those textbooks. If you want, you can please refer to that. So the way it is done is, first you compute second order partial derivative along the y direction, convolve with the image, and then convolve with the filter in the x direction. And then you will add the same operation which you performed in the y direction, you are going to perform in the x direction. So this is like the second order partial derivative in the x direction, and this is like your Gaussian in the y direction. So now you have, this is like the first 1D operation. This is again 1D. So this is the third one. This is the fourth one. So earlier you had like n square multiplications, but this reduces to just 4n multiplications. So that's a big optimization. Now, so given an image, first you perform Gaussian filtering. Gaussian filtering in x direction. This is Gaussian filtering in y direction. You will add those two values. That will give you like your filtered image. Now, for Laplacian of Gaussian filtering, given an image, first you compute the second order derivative in the y direction, and then your Gaussian in the x direction. Again, your second order partial derivative in the x direction, then your filter in the y direction. You add these two values, that will give you Laplacian of your Gaussian filter. Okay. Now coming back to algorithm, back to the algorithm of this edge detection. First, you have to compute the Laplacian of Gaussian. You can either use 2D filter, which will have n square multiplications, or you can use 4 1D filters, which will have 2n multiplications. Then you can find the zero crossings from each row. Then you can find the slope of the zero crossings. Then you'll have to apply some kind of threshold to mark your edges. So that's like the general algorithm which you will use. So for example, the same image again, you compute the Laplacian here and then convolve with the image. So this is the result you get. And if you find the zero crossings, you will find all the edges over here. So one important thing is, so now you're not doing like mean filtering, right? You're using Gaussian as a filter. So then there's a parameter which is like standard deviation, which you can vary. So if you use a very small standard deviation, so that will result in like a very like a thin Gaussian, something like PT, something like this. Okay. So what that is doing is that will only look into like a local neighborhood. So if you want to detect edges like which are very fine or very fine grained, we'll have to use a very small Gaussian. So these are the edges using a small standard deviation. And if you start increasing that, you can observe that the density of the edges is like reducing, and instead of local edges, you are getting higher level edges. And if you increase this further, so you can see that it's very sparse. Okay. So that was the effect of changing the standard deviation. So that was the third edge detector. Now let's move on to the final Canny edge detector. So again, the steps will be same. First, we'll have to smooth the image. Again, we will use a Gaussian filter here. Now, instead of second order derivative, we are still going to use first order derivative to filter the image. And then we will find the magnitude. So remember, like your Prewitt and Sobel, you were just following the same steps. Instead of Gaussian, you had mean filter. Then the second step is like, it's the same. And you computed the magnitude as well, but you didn't compute the orientation of the gradients, right? So that's the first change to the Gaussian filter. The second change is this orientation of gradient. And then because of that, what you have to do is they will also perform like this non-maximum suppression, and we are going to discuss this in detail. Now, in the earlier detectors, when you were using some threshold on the magnitude, there was just one threshold. But now we are going to use a different kind of threshold, which is called like hysteresis threshold. And in this case, we have two different thresholds. One is like high, one is low. Again, we are going to discuss that in detail. So Canny detector, if you compare this to Sobel or Prewitt, instead of mean, we have Gaussian filter. It's still single order derivative. We need the magnitudes, but we will make use of the orientation of gradients. And these are two extra steps which we can perform on top of this. So given an image, now since you are computing like first order derivative and your filter is Gaussian, what you can do is you can you know the optimization, you can directly apply the derivative on the filter. So this is like the derivative of your Gaussian, and I think this is an x direction. And if you look at this derivative from the top, it will look something like this. So you have like negative values here, and you have positive values here. And again, this is like a derivative in y direction. Now, what we will do is we'll apply this filter first in the x direction of this image, followed by applying this filter in the y direction. And then whatever result we got, we will use that to find the magnitude of the derivatives. Okay, so that's the derivative in x direction, that's the derivative in y direction. And if we use these two to find the magnitude, that will like square root of square of this and square of this, you will get the magnitude. Okay, so until now, it's almost similar to Prewitt and Sobel edge detector. The only difference being instead of average filtering, we are using Gaussian filtering. Now, what we will do is we will also make use of the edges of the gradients. And this is like a nice visualization of the edges. So each color is like representing one particular direction. And you can see that how the color is changing. So that's just representing the direction of the gradients. All right, so now as we discussed, we have two extra steps apart from that. The first one is non-maximum suppression. So let's see what this is. Now we discussed earlier, a good quality of an edge detector will be when we don't predict like too many edges at a surrounding. So we only need to predict the edges which are actual edges. And so this is kind of trying to refine that. Now, let's say we are at this particular location, Q, and we have detected an edge here. So what we will do in non-maximum suppression is we want to make sure that if Q is an edge, then in the surrounding, we don't have any other edge. And this will ensure that this is like the only edge and the correct edge. And we will do that based on the magnitude of this detected edge. And apart from magnitude, we will also make use of the direction of the gradient. So for example, in this case, if the direction of gradient is this one, so moving from P to R, what we will do is we will try to interpolate the values of these two pixels. And there are different methods. You can even interpolate, or you can just use the like assignment. If this point is close to R, if this R point is close to this location, you will just use this value. And if it's close to this one, you will just use this value. So that's one way. The other way is to just interpolate values of these two based on the position of this point. Okay, so if this point is just in middle of this and this, we'll just average these two values. And same for P. All right, and then what will happen is you will get values for P and R, which is kind of the magnitude of edge at this location and this location. And then you will compare that magnitude with this Q. Now what is going to happen is if the magnitude of both R and P is smaller than Q, which means that this Q is the maxima in this direction, then we'll keep this edge. Otherwise, if the value of the magnitude of the gradients is greater in R, either in R or either in P, we'll just make it 0, because then we will say that the actual edge is at this location, not at this location. Okay. So if the gradient responses at an R or P are smaller than Q, then Q is an edge. Otherwise, it is not. Now let's try to understand this with this visualization. So for example, this is an image, and if this is an edge, so at this particular location, if you will compute the derivative, the direction of your gradient will be somewhere lying around this position. So one thing to note is the direction of gradient is always normal to the direction of your edge. All right. So if your edge is in this direction, then if you will compute the derivative in x and y direction of that edge, what's going to happen is you will get something, you'll get the slope, right? And that angle of that slope will be along the normal. So for example, in this image, you have this edge, and then this will be the direction of the gradient. Now you have an edge at this location, okay? And you also have an edge at this location. So just ignore this one, just consider this one, x, y. Now this is the direction of your gradient. And the first point here is x prime, y prime. And the second point here is like x double prime, y double prime. What you will do is you will compare the magnitude of the gradients of this location with this and this. So if the magnitude is higher, you will keep this as an edge. Otherwise, you will just ignore it. So this is nothing like, this is simply what I described. So you can this just in the equation format. So you will keep the value of the edge if it's greater than x prime y prime, and it's also greater than x double prime y double prime. Otherwise, you will just mark it at as 0. Okay. So that was non-maximum suppression, and you will do that for all the pixel locations, for all the locations for which you have computed the edges. Now, after non-maximum suppression, you can see that this is something which you will get. So if you try to visualize what's happening here is the cases where you have thick edges. So it's saying like, it's giving you a lot of edges at this particular location, but essentially you should have only one edge. So it's kind of trimming the edges and also kind of refining them. Okay, so yeah, that was one extra step in your Canny edge detector. The second one is hysteresis thresholding. As I said earlier we used to only have one threshold, and we use that value. If it's greater than that value, we'll keep it. If it's lower, we'll just ignore it. In this case, we use two different thresholds. So let's see how it works. Let's say you have an edge, something like this, okay, and this is another edge. So I mean, this is not an actual edge. It's only plotting, I think, yeah. So this is only plotting the magnitude of each pixel location. So this is saying at this pixel location, we have an edge and the magnitude is about that value. And this magnitude is going down as we move here, but still we have an edge. And again, the magnitude is increasing. Again, so we have another edge where the magnitude is pretty low in all the locations. Okay, so what we do, and this will happen like for most of the cases in your image. What we will do is we'll have two different thresholds. One will be high, the other will be low. Okay, so now earlier we used to have just this high threshold, and what we used to do is if the magnitude of the edge is above this line, we will keep that edge. All right, so with single threshold would have edges like this will be considered an edge, and this would have been considered an edge, right? And all of this would have been ignored, and this would have been ignored. But in this case, we know that when edges are like continuous, right? They don't break in between. So we make use of that property, and what we do is we also define a low threshold. And the idea here is if we have a long connecting edge, which at some location where we have high magnitude, but at some locations we have a lower magnitude, what we'll do is we won't ignore this particular edge. So the criteria is even if the edge has a lower magnitude, if it's connected to edges with a higher magnitude, that will be considered an edge. So in this case, this whole thing will be an edge. Now let's consider this particular edge. So in this one, all of these pixel locations, they are like below high, but above low. So still they will be ignored because none of the connected pixels to this edge are clearing this particular threshold. Okay, so that's like two level of thresholding, which is called hysteresis. So this is again whatever I explained, just like in an algorithm form. So if the gradient or the magnitude of the gradient at any pixel is above high, that will definitely be an edge pixel. Okay, that's simple. If it's below low, then definitely that's a non-edge pixel. So in this previous graph, if any of the edge magnitude is below this low, no matter what, that will be a non-edge. Now the interesting thing is when an edge is between low and high. Now what we do is we first perform a connected component of all the pixel locations, which will connect like if two pixels are together or not, and then we will iteratively like scan all the edges which are connected via this edge pixel, and if part of it is above the high threshold, then all of that connected component is considered an edge. Okay, so let's go through like what this connected component means. Now this is just like a 3x3 image, and so all of these blue pixels, they are considered edges. And so a connected component is if a pixel is like connected in these 4 ways. So if it's next to this pixel, that's connected. If it's on top, that's connected. On the right, on bottom. This is called 4-way connection. This is called 8-way connection, and this is 6-way, and this can also be like along this diagonal. So this is like different properties of connectedness which are used when you compute your connected component. So 2 neighboring pixels are connected in these different fashions. So depending upon like what exactly you want, whether you want the connected component to be very dense, so then you will use this 8 connectedness. If like in between, then 6 connectedness, and even if the pixels are touching, then you will use this 4 connectedness. Okay. So yeah, so you compute your gradients, then you will use the threshold low high. So if it's above high, we call that a strong edge, and if it's below high but above low, we call that a weak edge. Now, then you perform connected components on that image or all those pixel values based on the gradient magnitude. And then what you do is you start from the strong edges, and then you will follow the weak edges as long as they are connected. Now, let's see like some results of the Canny edge detectors. That's the original image. So you can see like these are pretty nice edges when you compare this with like the earlier edge detectors we discussed. Now, again, so our smoothing kernel was Gaussian. So we saw that earlier as well. If we increase the value of standard deviation, then we'll move from like finer edges to coarse level edges. So it will be same for Canny as well. And the value which you want to choose, that will depend on the desired behavior, what you want. So yeah, if you want like large scale edges or like very coarse level edges, you will use the high value of standard deviation, otherwise a small value. All right, so that was all for edge detection. And we are going to revisit this topic of edge detection when we complete like our tutorial on deep learning. And then we will study like some of the methods which are based on deep learning and which can be used for edge detection in images. Now, just to give you an idea, so the Sobel and the Prewitt were around 1968. So these curves around here. And this green dot we discussed last time, this is like human level performance. And we want to reach this particular location. And you can see that after 2013, so these I think are like deep learning methods. So you can see that big, huge improvement over here. So these are like all classical approaches. And we are like, so this method is, I think it's not recent. It's from 2017 and it's very close to like human level performance, this blue curve here. And of course, we are not going to discuss this method. This will be like, I think, very complex for this course. We will pick, I think, either this 2015 CVPR paper, deep contour, or maybe deep edge. All right, so these are somewhere at this location. All right, so that's the end of our edge detection lecture. Any questions you have?